Okay, so when we last left off, we were discussing the nomenclature of compounds that contain polyatomic ions. So just as a refresher, polyatomic ions are ions containing multiple atoms with a net molecular charge. So I gave you this list of polyatomic ions that you needed to memorize, each with distinct charges. We'll be using these throughout this next section and throughout this chapter. Now, for polyatomic ion containing compounds, the nomenclature rules actually get a little bit simpler. So first things first, we write the name of our cation, which is our metal or polyatomic ion. You just write the name exactly as you see it. Now, if you have a non-metal anion, you write the name and you replace the ending with IDE. This is for non-metal atomic anions. If, and this is our exception now, if the non-metal anion, so in this case, if your anion is a polyatomic ion, you write the name of the polyatomic ion with no changes. So polyatomic ions, you write the name exactly as written in the table. No changes, no changing the ending to IDE. So let's look at an example. So if we have to name the following compound, so looking here, first we name our metal. So our metal in this case, our metal cation in this case is Ca, which is calcium. So you write the name calcium. Okay. Cn, cyanide, is a polyatomic ion, and we just write the name of our polyatomic ion, which is cyanide. Note, we write the name with no changes. Okay, let's look at another example. In this case, we have a non-metal, in this case, we have our metal cation, which is potassium. So first and foremost, we write the name of our metal, which is potassium. Next, we look and see, we in fact do have a polyatomic ion. So NO3 minus is known as nitrate. So this is potassium nitrate. Okay, perfect. Notice that we write the name of our polyatomic ion with no changes. So this is nitrate, not nitride. Okay, so now that we've seen a few examples, I'd like you to take a moment and attempt to name the following two compounds, and you can submit your responses in the chat or in the Canvas quiz for chapter 3, that is 3.12. In terms of capitalization, if you're using the names in a sentence, you don't capitalize either portion of the name. So in general, you keep everything lowercase when you're talking about chemical names. But that's mainly in the context when you're writing like a report and you mention a chemical's name. The capitalization rules aren't super important in terms of how you'll see this material presented in problems. As long as you're able to go from a name to formula and formula to name, you're good to go. But in writing, you'd actually keep both portions of the name lowercase. So let's spend about 2 to 3 minutes naming these two compounds, and you're welcome to submit your responses in the chat or using the Canvas quiz feature. Let's try to get a few more responses in the chat and via the Canvas quiz feature, and then we'll discuss momentarily. And if there are any questions during this time, don't be shy to message me in the chat or unmute and ask your questions. I'm already seeing some reasonable responses in the chat. Let's try to get a few more, and then we'll discuss momentarily. The Roman numerals are applied when we're talking about ionic compounds with a transition metal cation. And these transition metal cations have a variable charge. So the Roman numerals are used exclusively to indicate the charge of your transition metal. And we'll actually talk about that momentarily. Any other questions? I'm checking Canvas right now to see how everyone's doing on their quiz responses. So let's now discuss this problem. Let's now discuss each of these two examples. So in this first case, we have an ionic compound containing two different polyatomic ions. First of which we have NH4. What do we call NH4 plus? What is the name for this polyatomic cation? What is the name for NH4 plus?
Ammonium.
Ammonium, exactly right. So we would call this ammonium. And then SO4 2 minus. What is the name for that following polyatomic ion? SO4 2 minus, what do we call that? And you're welcome. Yep, sulfate. So this would be ammonium sulfate. Okay, let's look at this next example. So in this case, we have a main group metal cation, in this case, calcium 2 plus. So we just call this calcium. And then we have a polyatomic anion, which is PO4 3 minus, that we call phosphate. So the second compound would be named calcium phosphate. The only tricky part of these types of problems is that you have to be able to effectively name the polyatomic anions. Any questions on these examples? Any questions on these examples? Let's do a few more. Let's do a few more of these examples. And let's look next at hydrogen-containing polyatomic ionic compounds. Allow me to pull up, so I noticed there were a few typos in the previous set, so I corrected them. Let me pull up a corrected version so we can continue on with our lecture. So let's now look at another subclass of polyatomic ion containing compounds, and these are hydrogen containing polyatomic ionic compounds. So some polyatomic ions contain hydrogen atoms bonded to a quote unquote base polyatomic ion. So for example, if carbonate would be our base polyatomic ion, addition of a hydrogen results in hydrogen carbonate. Now there are a few key features to note. I like to think of this added hydrogen as quote unquote H+. So adding a hydrogen atom reduces the charge of the polyatomic ion by 1 per hydrogen atom. In the case of phosphate, we have the addition of 2 hydrogen atoms, so we call this dihydrogen phosphate. Di meaning 2. Okay, so let's talk about the procedure for naming hydrogen-containing polyatomic ions. So let's look at HSO4 minus. So first things first, we write the name of our polyatomic ion base. In this case, our base polyatomic ion is SO4 2 minus, and we call that sulfate. Okay. Next, we write the name hydrogen in front of the name of our polyatomic ion. So in this case, this would be called hydrogen sulfate. Now, suppose that there are 2 or more hydrogen atoms. In order to accommodate that and indicate that we have multiple hydrogen atoms, we add the appropriate prefix in front of the hydrogen term. So for example, H2 H2PO3 minus, since we have 2 hydrogens, we call this dihydrogen. And then we just write the name of our base polyatomic ion, which would be phosphate. Ite because it has 3 oxygens, which is 1 less than phosphate. Now, there's one warning I need to provide you in this section. If a polyatomic ion contains hydrogen and is neutral, it has 0 net charge, it is known as an acid. Acids have different naming conventions. So for example, HSO4 minus is known as hydrogen sulfate, while H2SO4, which as we notice has 0 charge, it's a neutral molecule, is known as sulfuric acid. So notice if it's a neutral species containing hydrogen and a polyatomic ion, you're dealing with an acid, and those have different naming conventions. Does that make sense to everyone so far?
What do you mean by neutral? Like the charge?
Yep, if the total charge is 0, then it's known as a neutral species, yes. So notice how our polyatomic ion containing hydrogen has a net charge, while our acid has 0 net charge. That is the key distinction to keep in mind between a hydrogen-containing polyatomic ion and an acid. And that determines what naming rules that you'll use. Yes. So for hydrogen phosphate, so for example, or hydrogen phosphite, if we have PO3 3 minus and we add 2 H pluses, so our overall charge will be -3 plus 2 times 1, which would give us an overall charge of -1. In order to calculate the overall charge of your hydrogen-containing polyatomic ion, you add the charge of your polyatomic ion to the charge of your hydrogen atoms. Does that make sense so far? Another way of thinking about it, we have 2 hydrogen atoms, so our charge becomes positive by 2 units. Okay, let's keep going with this idea, and let's name a few more compounds. So first and foremost, let's do a guided example where we name this batch of 3 compounds. So the first of which, first, let's look at our metal. So we have just a main group metal that we'll call lithium, just reading off from the periodic table. So looking at HCO3 minus, So CO3 2- is known as what? What do we call our polyatomic ion base? What do we call that polyatomic ion base? CO3 2-, what's the name for that? Carbonate, yep. Okay. However, since we have a hydrogen in our chemical formula, instead of calling it lithium carbonate, we'd call this lithium. And what do we fill in that blank? We call it lithium. Instead of lithium carbonate, it would be, yep, hydrogen carbonate. Exactly right. Oops, one moment. Let me just adjust the volume so that way I can hear you a little bit easier. Okay, perfect. Yep, this would be lithium hydrogen carbonate. Okay, so let's continue on with this example and let's name another compound. In this case, we have a hydrogen containing polyatomic ion derived from an atomic ion. So first we name our cation. In this case, this would be called calcium. Okay, next let's focus on our anion. So we have HS-, and let's look at our atomic ion base, which is S2-. And what is our name for S2-? What do we call this anionic species? What do we call this anion? S2-? It's not quite polyatomic yet. S2-, looking at it, how would we name S2-? Yep, exactly right. This would be sulfide. And since we have a hydrogen appended to our polyatomic ion, instead of calling it sulfide, we'd call it calcium hydrogen sulfide. Okay, let's do one more example. In this case, we name our cation, which is sodium. Looking at our anion, we have H2PO3-. Our base polyatomic ion is PO3 3-. We name our base polyatomic ion, which in this case is phosphate. Now, because we have two hydrogen atoms, what prefix do we use? Because we have two hydrogen atoms in our polyatomic ion, what prefix do we use?
Dihydrogen.
Yep, exactly right. So we call this sodium dihydrogen phosphate. Yep, that's exactly right. So now that we've covered a few examples, let's apply this idea to a set of problems where you're asked to name a series of hydrogen-containing polyatomic ions. And you're more than welcome to submit your responses in the chat, or you can submit them in Canvas Quiz 3.12.1. Either way is more than okay. It just allows me a method for checking the class's progress, and it gives me a way of getting a sense of how everyone's progressing through the problems. So let's take about 3 minutes and name the following 3 compounds, and you're welcome to submit your responses via the chat or via Canvas, just so that way I can get a sense of any common errors or anything I need to correct, and see if the class is speeding through the questions. But don't be shy to ask your questions in the chat, or unmute and ask your questions verbally. And we'll discuss momentarily. And I'm already seeing some reasonable responses in the chat. Let's continue on with this problem and then we'll discuss in a few minutes. I'm checking to see how everyone's doing on the Canvas quizzes. So the difference between sulfate and sulfite is that sulfate, which is the quote unquote, it's the 8 form, which is the one that you should memorize for this polyatomic ion series. So sulfate has, for example, 4 oxygens, while sulfite, the ITE prefix tells you that you subtract 1 oxygen. So then it would be SO3 2-. So ite tells you it has 1 less oxygen than the 8 form. Let's spend a few minutes working on this problem, then we'll come together to discuss in a few minutes. I'm seeing some reasonable responses in the chat so far. Let's try to get a few more responses, and then we'll discuss this problem. Spend about another minute to a minute and a half working through this problem, and then we'll discuss momentarily. Okay, so let's discuss the following example. So first and foremost, we name our metal cation, in this case, which is calcium. Then we name our polyatomic ion base, in this case, which is sulfite. And since we have a single hydrogen atom, we apply the prefix of hydrogen. So we have the full name of calcium hydrogen sulfite. Let's look at this next example where we have a polyatomic ion derived from an atomic species. So, in order to tackle this, first and foremost, we are going to write the name of our metal, which is magnesium. Next, we write the name of our atomic ion base. So P3-, what would we call that? What's the name of the atomic ion P3-?
Phosphide.
Yep, exactly right. So P3- is known as phosphide. So we write that out. The IDE ending clearly indicates that it's an atomic ion. Since we have a single hydrogen atom, we write the prefix of hydrogen. Perfect. So hydrogen, so to answer the question in the chat, what is the difference between hydrogen sulfite and bisulfite? So the bisulfite is an alternative naming convention. It's sort of the colloquial name. They're referring to the exact same compound. The method that I'm teaching you currently is the standard IUPAC method for naming these ionic compounds. And it is relatively common to see this IUPAC naming convention, although the colloquial name is accepted in certain cases. Does that make sense? On exams and quizzes, I would prefer you use the IUPAC method of naming. Perfect. So let's continue on now and let's look at the next compound. In this case, let's look first at our metal cation. Just one moment. Let's zoom in on our metal cation. Okay, so our metal cation in this case is Ag, which corresponds to silver. Now we name our polyatomic ion base, which is CrO4 2-. What do we call CrO4 2-? What do we call that? What do we call that? Chromate, exactly right. So then, as we have an appended hydrogen atom, we'd write this as silver hydrogen chromate. Do these examples make sense so far? Any questions on these examples? If not, let's continue on and let's talk next about ionic compounds that contain transition metals. So transition metals can adopt a range of positive charges. So for example, we can have copper plus, copper 2+, and copper 3+. So your transition metals in ionic compounds can have a range of possible charges. Now, most transition metals will adopt a +2 charge, but the charge of the transition metal must be explicitly noted to avoid ambiguity. So for example, if you say copper chloride, considering all the potential oxidation states of copper, all the potential charges of copper, you can be referring to everything from copper with 1 chlorine atom or 1 chloride ion, to a species with 2 chlorine atoms, to a species with 3 chlorine atoms. Now, to alleviate that ambiguity, we use a Roman numeral system. Okay, so first things first, we write the name of the transition metal cation, okay? So let's suppose in this example, we're naming CoBr2. So our transition metal cation would be Co, which is cobalt. So let's write that name. Next, what we have to do is we have to write a Roman numeral after the name of the transition metal, indicating the charge of the transition metal cation. Wonderful. Okay, so how do we do that? Well, given our formula, we can figure out the charge of each of our ions by reverse crossing our subscripts into the charge. Remember this discussion previously? You can also use the equation that I showed to calculate the charge of your metal cation. That in turn gives us cobalt 2+ and Br-, which checks out as bromine typically adopts a -1 charge. Everything is right with the world so far. So then, after the name cobalt, what Roman numeral do we need to put? What Roman numeral do we need to put? If our charge is 2, we put the Roman numeral for 2. That is saying cobalt has a +2 charge. Does this make sense so far? So this is why I taught you the method to figure out the charge of a metal or atom because you need it to name transition metal containing compounds. Now, the next set of rules concern your anion. If your anion is an atomic ion, you write the name of your anion and replace the ending with IDE. So to show an example of that, with COBr2, we figured out that the cobalt has a charge of +2, so we name this as cobalt 2, and then instead of bromine, we call this bromide. So the full name for this compound is cobalt 2 bromide. Now, suppose that you have a polyatomic ion at play. Then when you're writing the name of your polyatomic ion, you write the name of the polyatomic ion with no changes. So let's look at an example of that. So in the following compound, first and foremost, I'm going to write the name of my metal, which is nickel. Next, I'm going to reverse cross my charges to get nickel 3 plus and NO3 minus. Wonderful. So for nickel, what Roman numeral should I put in this example? For nickel, what Roman numeral should I put?
3.
3, yep. So this would be nickel 3. And then this NO3 minus, what do we call NO3 minus? What's the name for that polyatomic ion?
Nitrate.
Nitrate, exactly right. These salts, nitrate salts, are super common, and it's a very common polyatomic ion that you'll see a lot, especially in the lab. Why? Those are very easily handled ionic salts and ionic solutions. So the full name for this compound would be nickel 3 nitrate. Now, there's one exception, and we've already seen this before. Fixed charge transition metals, silver, cadmium, zinc. They form exclusively silver 2 plus, cadmium 2 plus, and zinc 2 plus. You do not have to specify the charge of the transition metal for a fixed charge transition metal. So this is a common trick question that you'll see, so just make sure you're being vigilant of that fact. Okay, so let's look and let's try and name the following compounds. So first and foremost, we have to do some charge analysis. So if we have Fe and SO3, we take our subscripts and we cross our subscripts into the charge. That in turn gives us Fe plus and SO3 minus. Now, if we go to our list of polyatomic ions and their charges, is this the correct charge for sulfite? Is this the correct charge for sulfite?
No.
So then, in order to correct our charges, we're going to multiply both of our charges by a common whole number. And what whole number do we choose?
2.
Yep. So that in turn gives us Fe2 plus and SO3 2 minus. Now we can name this compound. We write the name of our cation, which is iron. In our Roman numeral, because our charge is +2, we put a Roman numeral for 2. Again, I really want to emphasize this. The number in the Roman numeral is the charge, not the number of cation, it is the charge. Okay, now let's name our polyatomic ion, SO3 2 minus, we'd call that sulfite. So this would be iron 2 sulfite. Let's look at another example. Zinc iodide, okay? So in naming this, First and foremost, let's do our charge analysis. So we cross our subscripts. That gives us zinc 2+ and I-. So in naming this compound, we'd write the name of our cation. Do I need to put the charge? Do I need to put the charge for this compound? Do I need to include a Roman numeral? No, because zinc is a fixed charge transition metal. So common trick question that you'll see on ACS exams. Now, let's look at our anion. I-, it's an atomic anion. So how would we name I-? Instead of iodine, it would be what? Instead of iodine, it would be what? Instead of iodine, we'd call this
Iodide.
Yep, iodide, exactly right. So this would be zinc iodide. Perfect. Let's now look at another example. This one looks a little bit complicated, but follows the same logic. So first we do our charge analysis. So we have cobalt and we have HC2O4, 2. We cross our charges. That in turn gives us cobalt plus and cobalt 2+ and HC2O4-. Okay, so first we name our cation, which is cobalt. Then we specify the charge, which is 2. Finally, we name our polyatomic ion, and it's hydrogen containing. Okay, so we have to further unpack this, and let's look at C2O4 2-. What do we call this polyatomic ion? Oxalate. Yep, if you happen to be pre-med, oxalate salts are the principal component of kidney stones, if you're curious. So yes, this is oxalate. However, since we have a hydrogen atom appended to our polyatomic ion, instead of oxalate, we would call this hydrogen oxalate. So this is cobalt to hydrogen oxalate. So see how we can integrate all of our rules that we previously discussed into naming very complicated compounds. Now your goal is to be able to name compounds effectively, and in order to name a compound effectively, you have to classify it. Is this a transition metal containing? Does it have a polyatomic ion? What type of polyatomic ion? Those are the things you should be thinking about as you work through these examples. So let's take about 3 to 4 minutes and let's try to name the following compounds. And just remember, your charges need to be correct and reflective for your polyatomic ions and your atomic ions. So always make sure you're checking that your charges are correct for your anions in particular. And we'll discuss in about 3 to 4 minutes. You can submit your responses and questions via the chat or verbally, or you can try submitting your responses via Canvas through Canvas Quiz 3.13.1. If you look at Canvas through assignments, I have all the exercises that we'll be working on today sorted via chapter. And some students are pretty fast at these names. I already have a few submissions via Canvas. Thank you for doing that, as it really helps me see how the class is doing on these questions and anything I need to talk about during these discussions. If there are any questions while you're working through these problems, don't be shy to ask them verbally or in the chat. And don't be shy to message me your proposed responses, either via the chat publicly or privately. And so just so that way I can provide some feedback. And we'll discuss in about another 2 to 3 minutes. Let's try to get a few more responses before we discuss. So far, the bulk responses are looking pretty good overall from the class. Let's try to get a few more responses, and if there are any questions, I just want to give everyone time to work through these problems in about the same time scale that they'd be working through these problems on a typical exam or quiz. It seems like almost everyone has submitted their answer either via the chat or via Canvas. So let's now discuss this example. So first and foremost, AgClO4. So first we have to do some charge analysis. I just do this as a convention because it helps me both in this chapter, and it's a critical component of later chapters. Next, we write the name of our metal cation. In this case, our metal cation is silver. After we write the name of our metal cation, my question to all of you is, do we need to specify the charge? Do we need to specify the charge? Is that important? No, because silver is a fixed charge transition metal. It's on our list of 3 fixed charge transition metals. So we're done with our cation portion. Now looking at our anion, what do we call the polyatomic ion ClO4? I always remember it as a very explosive polyatomic ion. What do we call ClO4? Perchlorate, yep. So this is perchlorate with the per-8 prefix-suffix combination indicating the polyatomic ion with the most oxygen atoms. Wonderful, wonderful. Everyone did a great job with that. Let's now look at this next example. Again, we have to do some charge analysis. And this time you have to be a little bit careful. So this gives us lead plus and Cr2O7 minus. Now, is this charge for dichromate correct? Does this charge match the charge of dichromate or Cr2O7 in our table? Is that the correct charge? Do we have the correct charge for dichromate?
No.
Yeah, that's exactly right. The charge is not correct. So as a result, we're going to need to multiply both of our charges by a whole number. And what whole number do we choose?
2.
2. Exactly right. Exactly right. So then we write this as lead 2 plus and Cr2O7 2 minus. Now we're ready to name this compound. So we write the name of our cation, which is lead. Then we specify the charge of our metal cation. In this case, Pb2 plus, we put a charge of 2. So this would be lead 2. And then what do we call Cr2O7? What do we call that polyatomic ion?
Dichromate.
Dichromate, exactly right. So this would be lead 2 dichromate. Perfect. Oh, wait a moment. We have the correct idea, but when we crossed, this lead should be plus 2. And when we multiply it by 2, it should be plus 4. So this should be lead 4 dichromate. The 2 was obtained from the subscript of our dichromate. We multiplied both of our charges by 2, and that gave us lead 4 dichromate. So the key takeaway from this discussion is that you want to make sure that you're checking that your anion charge matches the known charge of your polyatomic ion, or it matches the known charge for your atomic ion species. Let's do another example. In this case, we have CrHCO3. So first, let's do some charge analysis. So we take each of our charges and we cross them. That in turn gives us chromium plus 3 and HCO3 minus. Both of our charges look good according to charge rules. So then we write the name of our metal, which is chromium, which is quite a famous metal, especially for the Los Angeles area. Now, we then have to specify the charge of our metal, which is 3. And then finally, for our polyatomic ion, it's a hydrogen-containing polyatomic ion. So first we name the base. So what do we call CO3 2 minus? What do we call CO3 2 minus?
Carbonate.
Yep. And because we have a hydrogen appended, we would call this hydrogen carbonate. Do these examples make sense so far? Any questions on these examples? If not, let's continue on. Now, this next skill is very important because in word problems, I'll be giving you the formulas as text descriptions. So then you need to be able to go from the name of a compound into the formula. So let's do just that. So let's suppose we're given the following name, scandium 3 hydrogen chromate. So just like before, we write out our cation. In this case, we have scandium. And what is the charge of scandium? What is the charge of scandium?
3 plus.
Yep, exactly right. And then hydrogen chromate. So we have chromate. So let's write that out. Chromate is CrO4 2 minus. If we add a hydrogen, if we plop on an H plus, that in turn would give us HCrO4. And then what happens to our charge? Is it going to be 2, 1, or 3? What's the charge of hydrogen chromate? And don't be shy to either provide a response verbally or in the chat, whatever you prefer. What would the charge be of hydrogen chromate?
I think it would be just -1.
Yep, exactly right. The charge, you add the charges together, -2 plus 1 is -1. Okay, so we write out the formula and charge of our polyatomic ion. And now all we have to do is we cross our charges into the subscripts. And that in turn gives us scandium HCrO4 3. There we go. Wonderful. Let's look at another example. In this case, we have cobalt 2 hydrogen phosphate. So we write out our metal cation with the charge. For hydrogen phosphate, so phosphate is PO3 3 minus. Oh, for phosphate 8, so PO3 3 minus would be phosphite. For phosphate, we add an oxygen, and that in turn gives us PO4 3 minus. And since it's hydrogen phosphate, we append on a hydrogen, and our charge decreases by 1. So we have HPO4 2 minus. Now we write out the formula of our polyatomic ion, which is HPO4 2 minus, and then we cross our charges, and that in turn gives us cobalt 2 HPO4 2. Now, is there something else that we can do here? Is there something else that we can do here?
We can simplify.
Yep, exactly right. So we're going to simplify this 2-to-2 ratio to a 1-to-1 ratio. Perfect, exactly right. Let's now look at another example where we have iron 3 bromite. Okay, so first we write out the name of our metal cation, which is Fe3+. Now for bromite, would someone like to provide the formula for bromite? It's derived from the bromate ion, and this is in our list of polyatomic anions. Would someone like to try to provide a formula for bromite? You may have to refer to your table, and it's okay to keep your table of polyatomic ions handy as a cheat sheet while you're learning these examples. So for bromite, yep, it would be BrO2 minus, exactly right. So now we write out the formula. Just for your reference, bromate is BrO3 minus. So then bromite has one less oxygen, which is BrO2. Then we cross our charges, and that in turn gives us Fe BrO2 3. There we go. So we've effectively provided the formula for each of these 3 ionic compounds that contain a transition metal. So in fact, it's a little bit easier than your main group metal examples. So let's now apply our knowledge to the following examples. These are found in Canvas Quiz 3.13.2. You're welcome to work through your examples in the notes and then submit your responses either in the chat or via Canvas, just so I can get a sense of how everyone's doing on these problems. And we'll discuss in about 3 to 4 minutes. So try to write the formula and select the correct formula for the following compounds. And we already have some responses, surprisingly, via Canvas, but let's give everyone about 3 to 4 minutes to work through these examples. And if there are any questions, don't be shy to ask them verbally or in the chat. And don't be shy to submit your responses via Canvas or in the chat publicly or privately, just so that way I can provide feedback. And if there are any questions, don't be shy to ask them in the chat or verbally. Let's try to get a few more responses in the chat or via Canvas, and then we'll discuss. Overall, everyone's doing quite well on Canvas, and we'll discuss in about 2 minutes. Everyone's doing quite well from what I see on your submissions via Canvas. We'll discuss in about another minute to a minute and a half. And if there are any questions, and if you want to submit your responses in the chat, you're more than welcome to, and I can also provide feedback that way. And the responses submitted in the chat look quite good. And we'll discuss in about another 30 seconds to a minute. And the real important part behind these problems is not just what is the answer, but making sure you have the correct process to reach the answer. You may not see these exact compounds on the exam, but you'll see something that follows very, very, very similar logic. Okay, I'm seeing a lot of wonderful responses both in the chat and via Canvas. So let's discuss. So vanadium 5, vanadium V, which is sort of funny because it's a symbol and then a Roman numeral, which is the same symbol. So let's write out. So we have vanadium 5, which is 5 plus. Oxide. Oxide is so IDE tells us we have an atomic ion, and that is O2 minus. Where did we get O2 minus from? Oxygen's a 6A element. 6 minus 8 gives us -2. Okay, so now we cross our charges. That in turn gives us V2O5, which is the formula for vanadium oxide. Okay, let's look at this next example. Titanium 4 hydroxide. Okay, so the charge of titanium is +4. Hydroxide, would someone like to provide the formula for hydroxide? This is a polyatomic ion, and it's one that you should know because it's super common. Probably one of the most common polyatomic ions you would see in this class.
OH minus.
Yep, exactly right. We have OH minus. So let's now cross our charges. That in turn gives us titanium OH4. Perfect. Now let's continue on with iridium 2 iodide. Okay, so first and foremost, let's write out our cation. Iridium is IR 2, so it has +2. Now iodide is a polyatomic ion. Would someone like to provide the formula for iodide? So ITE tells me we're dealing with a polyatomic ion. Looking at your list of polyatomic ions, would someone like to provide the formula for iodide? Yep, IO2 minus. So just for your reference, iodate is IO3 minus, while iodide is IO2 minus. Now that we have our formulas and the charges, we cross our charges into the subscripts, and that in turn gives us iridium IO2, 2. So this is Iridium 2 Iodide. Does this example make sense to everyone? Any questions on this example? If not, let's continue on with a few more problems. Now we're going to talk about another subclass of compound that we call a hydrate. Now, a hydrate is a compound consisting of an ionic compound and associated water molecules, hydro-water hydrate. We call an anhydrous compound, an anhydrous compound is a hydrate without water molecules. Now, the hydrate and the anhydrous form of a compound are entirely different chemical compounds. It's not just wet ionic salt. So to give you an example of this in a very practical term, so if we have, for example, cobalt chloride hexahydrate, so this dot indicates associated water molecules, so this would be our hydrate. The anhydrous form of this compound has an entirely different color and an entirely different molecular mass, as indicated by the fact that I've drawn these formulas in two different colors. So the hydrate and the anhydrous form have different masses and they have different properties. In this case, we see that they have different colors. So let's talk about the rules for naming hydrates. So first things first, you write the name of your ionic compound, and then you write out a prefix for the number of water molecules. These prefixes are shown here. And then finally, you write the name hydrate at the end of the name. So let's break down a guided example where I've already filled in the correct answer. So in this case, we write the name of our ionic salt, which is cobalt 2 chloride. We have a total of 6 water molecules absorbed or associated with our ionic compound as part of this hydrate formula. So we go to the table, 6 corresponds to hexa, and then we write the name hydrate at the end. So this is cobalt 2 chloride hexahydrate. Let's look at another example. And we'll make up one in this case. Let's do lithium sulfate. Let's do this with 2 water molecules associated. So first things first, we name our ionic compound. In this case, this would be called lithium. Let's make it sulfate just for some variety. Sulfate. And now for the new part. This is the new part. Since we're dealing with a hydrate, if we have 2 water molecules associated, what prefix do we use? What prefix do we use for 2 water molecules?
Di.
Yep, exactly right. So this would be called lithium sulfate dihydrate. And this last part is the only thing that's new about naming hydrates. The only unfortunate part is you have to be really comfortable naming ionic compounds to name hydrates. Let's do a few more guided examples. So first and foremost, we have the following compound. Now I see a polyatomic ion, and I also see a transition metal. So that sets off a red flag to me that I need to do some charge analysis. So I take my subscripts, I cross them up into my charges. That gives me copper plus and SO4 minus. Is that correct? Does this charge for sulfate, SO4 minus, look correct to everyone?
No.
No. So then we're going to have to multiply both of our charges by 2. That gives us copper plus 2 and SO4 2 minus. Now we can name this compound. We write the name of our metal, which is copper. Since it's a transition metal cation, we specify the charge with a Roman numeral. Then, since we have a polyatomic ion, we write the name of our polyatomic ion with no changes. So this is copper 2 sulfate. Now, since we have 5 water molecules, what prefix do we use? Since we have 5 water molecules, what prefix do we use?
Penta.
Penta. So we call this copper sulfate pentahydrate. We actually will likely be handling this compound when we do our composition of a hydrate laboratory. It's a nice distinct blue solid. It makes these deep blue solutions as well. Let's keep going now with a few more examples. So in this case, we have LiHSO4. So we write the name of our cation, in this case, lithium. Now, SO4 2 minus we know is sulfate. However, if we have an appended hydrogen, so HSO4 minus, we call this polyatomic ion hydrogen sulfate. And now for the part that's new. If we have 1 water molecule, what prefix do we use? If we have 1 water molecule, what prefix do we use?
Mono.
Yep, so this is lithium hydrogen sulfate monohydrate. Perfect. So let's do another example, this time where we're writing the formula of a hydrate from the name. Okay, so we're given the name nickel 2 carbonate tetrahydrate. Okay, so let's get to work on that. So we know the charge of nickel is 2+. We know that carbonate has a formula of CO3 2 minus. Remember, the 2+ for nickel was obtained from this Roman numeral. Okay, so first let's focus on the ionic compound. We cross our charges into the subscripts, and that in turn gives us Ni2CO3 2, and then we can simplify this to NiCO3. So this is nickel 2 carbonate. Okay, so next we have to deal with our hydrate portion. So we put a dot to indicate associated water molecules. And for tetrahydrate, tetra tells us we have how many water molecules. Tetra tells us we have how many water molecules. And don't be shy to look at the table on page 36 of the notes. Tetra tells us we have how many
4.
water molecules. And just so that way you're getting used to the table, let's go to the table together. We see tetra corresponds to how many? 4. Yep. So we have 4 water molecules. So it's nickel carbonate with 4 associated water molecules as part of our hydrate formula. Any questions on these examples? Any questions on these examples? The reason why we don't put parentheses is that if there's just one of a polyatomic ion, you don't need to specify the number. Just like, for example, a subscript of 1 isn't included, right? I mean, it's not entirely wrong if you want to put carbonate in parentheses, but typically if there's only one polyatomic ion, we don't put it in parentheses. Does that make sense? Perfect. So let's keep going now, and let's try to apply what we've covered in these previous examples to a new set of problems. In this case, you can submit your responses via the chat or via Canvas, looking at Canvas Quiz 3.14. So in this case, you're asked to name 2 hydrates, as well as write the formula of 1 hydrate. And we'll discuss in about 3 to 4 minutes. Don't be shy to submit your responses via chat or via Canvas, and we'll discuss momentarily. And if you have any questions, of course, don't be shy to ask them via chat or via Canvas. So checking Canvas, I'm seeing a fair number of reasonable responses so far. If there are any questions students have when working through these problems, don't be shy to message me in the chat. And remember that the rules for naming ionic compounds depend on whether it's a polyatomic, depends on whether you have a polyatomic ion, a transition metal, a fixed charge transition metal, or a main group metal. So we'll discuss in about another 1 to 2 minutes. And if there are any questions, don't be shy to type them in the chat. I'd like to see a few more responses in the chat or via Canvas, just so that way everyone can look at their solution, compare to the solution that we cover as a group, and then make any changes to how they solve these problems. So we'll discuss in about another minute to a minute and a half. But overall, the class is doing quite well on these problem-solving sessions, which is quite encouraging. Let's try to get a few more responses, and if there are any questions that I can answer to help address and assist you solving these problems, do not be shy to ask. Okay, so let's now discuss this problem set. First and foremost, let's name our ionic compound. I see a transition metal, so immediately I have to do some charge calculations. So I have iron and acetate. I reverse cross my charges. That gives me iron 2+, acetate, which has a -1 charge. That matches the tabulated charge of acetate. Everything's good to go in that respect. Okay, so now we're ready to name this compound. We write the name of our transition metal, which is iron. We place the charge in Roman numerals. And then we write the name of our polyatomic anion, in this case, which is acetate. Now we're ready to name the hydrate portion. So we notice that we have 4 associated water molecules. So 4 corresponds to the prefix of tetra. So this is iron acetate tetrahydrate. Okay, let's look at this next example, which was slightly problematic. So looking at zinc. So zinc is a transition metal, but what type of transition metal is zinc? And this is where you have to recall a list that I gave you. So for zinc, what type of transition metal is zinc? Is it
Fixed.
Yep, zinc is a fixed charge transition metal. And as a result, we do not have to specify the charge of zinc when naming it. So we'd write the name of our cation, which is zinc, the name of our anion, which is nitrate. And now for the new part. We have 6 water molecules. So what prefix do we use? What prefix do we use? 6.
Hexa.
Yep, so we call this zinc nitrate hexahydrate. Wonderful, wonderful. Just remember your fixed charge transition metals, you don't need to specify the charge with a Roman numeral. Okay, let's try to write a formula now. We have samarium 2 iodide monohydrate. So we write out the formula of our cation, which is samarium. Iodide, so IDE tells us that we have an atomic ion derived from iodine, which is I-. The charge of samarium is 2+. We cross our charges, that gives us SMI2. Monohydrate. So how many water molecules? Mono tells us we have how many water molecules?
1.
1, yep. So it's SMI2.H2O. Perfect. Any questions on these examples? Everyone did quite well from the polling via Canvas, so I'm quite impressed so far. If there aren't any other questions, let's keep going and let's talk about the elephant in the room, which are acids. So let's first look at the nomenclature rules for binary acid. So a binary acid is a neutral compound, no charge, containing exactly 2 different elements, one of which is a hydrogen and the other of which is a non-metal. Okay, now here's an important thing to note. How you name an acid and how someone talks about an acid can really give you a sense of how dangerous they are. Pure binary acids, so the really pure, 100% pure binary acids are gases. So HCl gas is a pure binary acid. And to name binary acids in the gas phase, first we write the word hydrogen. Okay. Then we write the stem of the second element and we change the suffix to IDE. So chlorine we'd write the chlor stem, and then we change the ending from chlorine to chloride. So hydrogen chloride is referring to HCl gas. However, we don't typically handle binary acids in their gaseous form, as that's quite dangerous. So most binary acids are handled as aqueous solutions. Now, to name aqueous binary acids, first and foremost, we write the prefix of hydro. Okay, so we write the prefix of hydro. We write the stem of the second element, and we change the suffix, we change the ending to IC. So chlorine turns into chloric. And now, as it is an acid, we write the word acid at the end of the name. So hydrochloric acid is referring to HCl with an aqueous symbol. Does this distinction make sense to everyone? Does everyone understand the process for naming binary acids and how the naming rules depend on the state, whether it's in the gas phase or whether it's aqueous?
Yes.
So most importantly, this aqueous naming convention is the most important that I want you to know, because we're going to be dealing with chemicals in this class primarily in aqueous solution. You should know how to name the gas phase binary acids, but I really, really want you to know how to name the aqueous binary acids. Yes, the suffix of IC is based on the fact that our acid is aqueous. Yeah. So these are the naming rules for binary acids in the aqueous phase. Perfect. So let's look at a few examples. Things are best learned via practicing and applying these concepts. So allow it 1 second. Allow me one moment just to quickly reset Zoom and not reset Zoom, but reset OneNote, just so that way it's a little bit smoother during the transitions. Okay, here we go. Now let me share the screen again. Okay, so let's look at the next few examples, and let's do a few guided examples where we write out the name and formula of a range of binary acids. Let me zoom in so the view is a little bit better. Okay, so first and foremost, let's name the following compounds. So we have an aqueous symbol, so we're going to use the rules for aqueous binary acids. So first and foremost, we see in order to name an aqueous binary acid, we start with the prefix of hydro. Now, fluorine has a stem of fluor. So we write our stem. Then we replace the ending, since it's an aqueous acid, we replace the ending with IC. And then as it is an aqueous acid, we write the ending of the name with acid. So this would be hydrofluoric acid. Now, looking at this next example, we have a gas phase binary acid or a pure binary acid. So we're going to have to use the rules for the gas phase binary acids. So in this case, we write the prefix hydrogen. Then we look at our anion, in this case, which is sulfur. Now we take our stem and we add the ending IDE. So sulfur turns into sulfide. So the name for this compound would be hydrogen sulfide. Does this example make sense to everyone? The key distinction, because we're in the gas phase, we use the ending IDE instead of IC.
So you wouldn't put di in front of it because di is only used for.
Di is only used for hydrogen containing polyatomic ions. That's exactly right. Did that answer your question?
Yeah.
Perfect. So let's now try to write a formula from the name. So hydrobromic acid. So I see the IC ending and the acid ending. So it's clearly going to be in the aqueous phase. For hydrobromic, hydrogen is H+. Bromic is derived from bromine, which is Br-. We take our charges and we cross them, and that in turn gives us HBr aqueous. Does this make sense to everyone? Any questions so far? If not, let's try to apply what we've learned to the following 3 questions. So let's take about 2 to 3 minutes and let's name the following compounds. You can submit your responses via Canvas Quiz 3.15 or in the chat, and don't be shy to ask questions via unmuting or in the chat. And we'll discuss in about 3 minutes. And if there are any questions, again, don't be shy to ask. And the responses I'm seeing in the chat look good so far. And if you've already attempted the Canvas quiz, you're more than welcome to message me your corrected responses, or you can reattempt the quiz once you've seen how we ran through these problems. Note the quizzes are always open for multiple reattempts for practice, as the whole point is to attempt some problems, see whether your logic was correct or incorrect, modify your logic, and then try these problems again. And if there are any questions, and just make sure you include the state symbol for the 3rd problem. So this one right here, make sure to include the state symbol. And the responses I see in the chat look good so far. Let's try to get a few more responses via Canvas. And after reattempting these questions, the class is doing substantially better throughout this problem-solving session. So it's quite encouraging so far. We'll discuss in about another minute to a minute and a half, and let's try to get a few more responses via Canvas or in the chat. Just so that way I can understand where the class is at. And it looks like we have almost everyone providing a response via Canvas or in the chat. So let's discuss these problems now. And as you notice with nomenclature, the more rules that we have for all these different compounds, the harder it is to keep them organized. So really focus first and foremost, classify your compounds. So I see I have an acid and it's an aqueous acid and it's binary. Wonderful. So I'm following the binary acid naming rules for the aqueous binary acids. So I write the prefix of hydro for aqueous binary acids. Then S is sulfur, but since it's aqueous, instead of sulfur, we change the ending to IC. So this would be sulfuric. So this is hydrosulfuric acid. Now, note this hydro prefix is critically important. This hydro prefix indicates that we have a binary acid. So it's an important part of the naming conventions. Let's look at the next example, HI, aqueous. Again, it's an aqueous binary acid, so we write the hydro prefix. Then I is iodine. So iodine turns into iodic acid. And then because it's an aqueous binary acid, we add the ending acid at the end. So if it's aqueous and it's a binary acid, the IC ending should be included. Do these examples make sense so far? Okay, let's look at another example. Let's try to write the formula from the name. So hydrogen selenide. So I see an IDE ending and a hydrogen prefix. So I see it's in the gas phase. Hydrogen is H+. Selenide is derived from selenium, which is Se2-. This is obtained because selenium is a 6A element. 6 minus 8 is -2. We cross our charges, and that in turn gives us H2Se gas. This is hydrogen selenide. You'd certainly know if you're handling hydrogen selenide as it smells terrible. Any questions on these examples for binary acids? Certainly a little tricky keeping everything straight, but I find that you'll be applying these nomenclature rules throughout this class. So this is really something that can pay off a lot in terms of points on the ACS and exams. So with that established, let's now look at our second to last class of compound, which are the nomenclature rules for polyatomic acids. Now, polyatomic acids are compounds containing hydrogen and a polyatomic ion. Oops, that's the wrong pen in that case. Now, a key feature of polyatomic acids that I'd like you to remember is that they are neutral. They have 0 net charge. Another subclass of polyatomic acids are your oxy acids. These are acids containing hydrogen, oxygen, and one other element. So let's look at how we name a polyatomic acid. So let's look at the example of HNO3. Okay, so in this case, first and foremost, you write the name of the polyatomic ion. Okay, so we'd call this nitrate. As our second example, let's look at HClO2, which is chlorite for our polyatomic ion. And now, depending on the ending of your polyatomic ion name, you follow two branching set of rules. If the ending of your polyatomic ion name ends in ITE, you replace the ending with OUS. So for example, ClO2 minus goes from chlorite. When you have HClO2, we name it with chlorous. ITE to OUS. If your polyatomic ion name ends in ATE, you replace the ATE with IC. So for example, nitrate, ATE. If it's a polyatomic acid, we name it as nitric. Finally, we write acid at the end of the name. So for example, HNO3 would be called nitric acid. HClO2 would be named chlorous acid. Notice, critically, we do not have the hydro prefix. It's just nitric acid and chlorous acid. Do these examples make sense so far? Let's look at a few special cases. So for sulfuric acid, sulfate turns into sulfuric. So H2SO4 would be called sulfuric acid. Likewise, for phosphate, phosphate turns into phosphoric. So H3PO4 would be known as phosphoric acid. The reason why we don't have a hypo is because ClO is known as hypophosphite. So notice that chlorite has one more oxygen than hypochlorite. Sorry about that. So the hypo prefix indicates the polyatomic ion with the least number of oxygen atoms. Notice how chlorite has one more oxygen atom than hypochlorite. Did that address your question? And the reason why we don't have the hydro prefix is because it's a polyatomic acid. Does that make sense? Perfect. So let's take a look at the following examples and let's try to name the following compounds. So H2SO3. So first and foremost, we look at our polyatomic ion, which is SO3 2-, which is sulfite. We have the ITE ending. So in our polyatomic acid, sulfite turns into sulfurous, and then we write acid at the end of the name. So polyatomic acids aren't that bad to name if you know all the polyatomic ions. Let's look at another example. So CH3CO2 minus is known as acetate. So what the ATE ending is replaced with IC. So when we look at our polyatomic acid of CH3CO2H, we'd call this acetic acid. Let's do another example. Again, we look at the polyatomic ion, in this case ClO4 minus. This is known as perchlorate. We have an ATE ending, so we replace it with IC. So HClO4 would be called perchloric acid. Do these examples make sense to everyone so far? Do these examples make sense to everyone so far? Now let's focus on naming the following compounds, and let's work on this and apply what we've learned in the following problem-solving set. You can submit your responses via the chat or via Canvas quiz 3.16. We'll discuss these examples in about 3 minutes. And don't be shy to message me via the chat or unmute and ask any questions you have about this content. And don't be shy to submit your responses via Canvas or via the chat. So the 3.16 has 2 parts. We're going to look at the first set of 3 questions right now in this first 3-minute problem solving exercise, and then handle the second batch of questions in a second exercise. And looking so far, I see a reasonable number of responses via Canvas. Don't be shy to submit your responses via Canvas or via the chat. And we'll discuss this example momentarily. Spend about another minute to a minute and a half. And if there are any questions, again, don't be shy to ask. See a reasonable sampling of responses via Canvas in the chat. We'll spend about another 30 seconds on this example, and then we'll discuss these first 3 questions. Okay, so let's discuss this example. So HBRO, okay? So let's look at our polyatomic ion, which is BRO minus. This is known as hypobromite. Okay. Now we have the ITE ending, which is replaced with OUS. So HBRO is hypobromous acid. Let's look at another example, H2C2O4. So C2O4 is known as oxalate. ATE is replaced with IC. So H2C2O4 2 minus, is known as oxalic acid. Let's look at another example. Cr2O7 2 minus is known as dichromate. The ATE ending is replaced with IC. So H2Cr2O7 is known as dichromic acid. Do these examples make sense so far? Any questions on these examples? Let's keep going then. So let's tackle the following guided examples where we write the formula for each of the names. So for example, chlorous acid, the OUS ending is converted into ITE. So it's derived from the polyatomic ion of chlorite. Chlorite is ClO2 minus. So chlorous acid is obtained by taking H plus, writing our polyatomic ion formula, and then crossing the charges. That in turn gives us HClO2. Let's look at another example. Carbonic acid, IC is traced back to ATE. So carbonic acid is derived from carbonate, which is CO3 2 minus. To obtain the formula of carbonic acid, we write the charges of each of our ions, and then we cross the charges into the subscripts. That in turn gives us H2CO3. Again, just remember to get the formula, you write the charge of each of your ions, and then you cross the charges. So to apply this example, let's continue our problem solving session 3.16. Your responses can be submitted in Canvas quiz 3.16. As I've noticed people are already working on it. Let's spend about 1 to 2 minutes just revising our answers for these problems and going through and just double checking our work and calculations. If there are any questions that you got incorrectly, now would be a good time to reattempt them with this information and with these examples in mind. And we'll discuss in about 1.5 to 2 minutes. And if you have any questions or if you want to submit your responses privately via the chat, I'll be more than happy to provide some feedback. And the responses in the chat look reasonable so far. Let's try to get a few more formulas complete in the chat. I see almost the entire class here has provided responses via Canvas. That's perfect. And I see overall everyone's doing quite well on these sets. So I feel comfortable now discussing these examples. So looking at nitrous acid is derived from nitrite, which has the formula of NO2 minus. We then write out the charge of H plus and NO2 minus and cross our charges. That in turn gives us the formula HNO2 for nitrous acid. Let's look at phosphorus acid. The OUS is derived from ITE, so it's derived from phosphite. Would someone like to provide in the chat the formula of phosphite? What is the formula of phosphite? Recalling our table of polyatomic ions, it's PO3, 3 minus. So writing the charge of H plus and the charge of phosphite and crossing our charges, that in turn gives us H3PO3. Perfect. So this is phosphorus acid. Finally, let's look at permanganic acid, derived from the IC ending turns into ATE, and it's derived from permanganate, which is a common oxidizing agent, which is of the form MnO4 minus. We write the formulas of each of our ions, and then we cross the charges to give us HMnO4. Any questions so far on this example? Any questions so far on this example? If not, let's continue on. We will, as we're at the end of our allocated lecture time, we're going to take a 40-minute break and then resume, and we'll finish up this lecture portion for chapter 3 in lab. It should only take us about 30 minutes in lab to clean this up. Then we'll discuss the laboratory for today and do a run through of the laboratory together via Zoom. So we'll take a break for lab and then we'll finish off this discussion.